My name is Chuck Bunting, and I'm Associate Dean of Research at the College of Engineering, Architecture, and Technology at Oklahoma State University. And I have the privilege of working with faculty and students who are eager to do more than just move the needle in research. At OSU, engaging in research has never been more exciting. OSU has a long tradition of working on transportation research problems with ODOT, Federal Highway, the FAA, and other local and federal agencies. Oklahoma State University has been a long partner with the University of Oklahoma in transportation research and work development to what used to be the Oklahoma Transportation Center, and now through the Southern Plains Transportation Center. Oklahoma's new Cooper Lab for Structural and Materials Engineering has been in operation for 3 years now. Most of the research conducted there at the Cooper Lab is directly linked to Oklahoma transportation and, as we saw from the Menti results earlier, concrete. That was the big word there. I don't know if you'd seen that in that slide. So if you ever get a chance to visit Stillwater, make sure that you get to visit the Cooper Lab. Make sure that you also take a look at the posters during the break. The partners from the Southern Plains Transportation Center and others highlight all the great work from the students across the state. And now to our session. We have an interesting set of presentations this morning, and let's get right to it. Our first speaker is going to be talking on the detection and incorporation of secondary accidents in speed, travel, time data sets for performance analysis. Presenters Hazem Refai from the University of Oklahoma, also co-authoring with Samir Ahmed at Oklahoma State University, as well as a long list of others from OU. Ahmed?
Thank you, Chuck. Well, good morning, everybody. My name is Hazem Refai, and I need to acknowledge some of the students in there: Naeem, Varun, Siraj, Munzir, and Jim Yao. I encourage you to go and look for a couple of demonstrations that we have there. One for a sensor, an intelligent vehicle count sensor, and the other one is for the presentation, or similar to the presentation I'm going to do here, which is the NPM RDS data. So the motivation, the content of this presentation is going to be the motivation of the work, then talk about a little bit of primary, secondary incidents, how it's defined by the FHWA, detection algorithms that we put together for a model development, and then some sort of a artificial neural network, ANN, to validate the accuracy of detection of secondary accidents. And we'll talk about a graphical user interface that we have built for this project. And we integrated it with the NPM RDS data that the state hold. And I'll talk a little bit about that just for one slide, and then introduce you for the GUI. And then when we get time, we'll talk about factors influencing secondaries of the project, or for the accidents that we have tested or worked on. So the motivation, FHWA says that 20% of the crashes are secondary accidents, and looking at 40,000 crashes per year, 40,000 fatalities per year, 20% is a lot, or 18% for fatalities is a lot. Secondaries, as we tested, and you'll see some of the examples that I brought here, you'll see secondary that always more severe than a primary accidents, and so they have the issue of prolonging congestions, delays, and so on. And then if we are able to go and mix the two databases, the NPM RDS database, which is the National Performance Measurement data set provided by FHWA, and accidents, we should be able to go and figure out the causes that really lead to increase of secondary accidents. And if we identify causes of secondary accidents, maybe we could really deploy some measures that would prevent these accidents from happening, so reduce the 80% fatalities. And so the incorporation of that with the NPM RDS tools I'll talk a little bit about that too. So the primary and secondary incidents, I'll just read the TIM, the Traffic Incident Management definition by FHWA. It's the number of unplanned incidents beginning with the time of detection of the primary incident when one incident occurs as a result of an original incident, either within the incident scene or within the queue in either direction. So there is a primary accident that occurred, and then due to that accident, maybe a buildup of a queue that causes a secondary accident to happen, or maybe, drivers been in the queue for long. When they clear the primary scene, they speed up, and you'll see a forward accident. You might have the opposite direction traffic, slowing down to look and cause an accident, secondary accident. In our case right now, we're looking at more or less, I'll give you an example of the forward. They called it, I was presenting at ODOT once, and they call it rubberneck, people that drive and see an accident and they just look around and see that. So the idea is, how do you draw that space, the length and the time within which any accident that occur is going to be labeled as a secondary accident. So now you have to run through the incidents or accidents and identify, label, classify as a primary, which is easy if you just scan through the data and you find an accident that had no previous accident or no relation to any other accident, you could call it primary. And now, in the process, you have to create some sort of a space in the spatial domain and the time domain within which, if an accident occurred, that you're going to label it related to that primary accident. So what we did, we went to traffic engineering and we took access to the database, or we had an access to the database, and downloaded a database from the website and started extracting the data. And so with that, we started looking at what data we have available and how we're going to do the space. How do we go and define our spatial temporal influence in there? So you're going to look for location, where is the location of the accidents, and create some sort of a proximity to that accident. Look at the traffic intensity, the flow in and the flow out within the segment within which the primary accident happened. Then determine the effect of the accident, the primary accident, on the highway, which is going to affect the capacity of it. So if I have 1 or 2 lanes blocked due to the accident, then I lost 2 lanes. And so if the average traffic is still coming in as it's regularly coming, then you're going to have a queue building up. And that causes the space to grow, the length to grow. And then the average time a vehicle that stays in the queue is going to grow up to within which that if an accident happened, I'm going to label it as secondary. So I look at the effect, we look at the effect, then take these effects, the capacity, the traffic intensity, and so on, into a queuing algorithm that calculates the length of the queue based on an average length of a car. I'm going to say the average number of cars is going to be, given the flow-in rate is going to be so many, and we put a length of 4 meters for a car or so on, so you build the space. And then graphically plot it and look at that. So the queuing mechanism, there are many queues that you could use to the analysis. You can do deterministic, which is the rate of traffic coming as a deterministic, fixed. Or you could do a memoryless, which is not related to the minutes before. And so you'll have some sort of a memoryless, which is an exponential time of arrival, or a Poisson time of arrival, exponential inter-arrival time that is coming in. And you'll have the N, which is the number of lanes that service that highway, that road. And so you apply that, and you apply some sort of an intensity. You have a model for your peak hours, the morning peak hour and the afternoon peak hour. So if an accident happened and a peak hour is going to have more damage or more delays than an accident that happened off-peak hour because of the traffic intensity that comes in there. So what we did, the traffic engineering database did not have really in its database, because it's extracted from police reports, that how many lanes were closed. So I talked with my friend Alan Stevenson, and I said, well, Alan, we have a database, but it's missing this information, and it's important for us, for the project, to figure out how many lanes got closed. And he said, well, there is another database called incident database that his group collects, that the police officer writes after they report an accident. They go onto their computer and enter, and one of the parameters they enter is how many lanes that are closed. So we took all of the accident database, that's from the traffic engineering group, the dock ID, the highway name, the street location, collision time, number of vehicle involved, number of lanes in the highway, the damage extent, and you have from 1 to 5, and 1, no damage, almost, to a 5 where there is a damage and a fatality in there. And then from the incident data from Alan, we received the highway name to match these, the street and location, collision time too that is reported, and lanes closed that they had in there. And so given that too, we started looking at, well, there are 2 different databases, and we wanted to start looking at meshing the ones that match between the 2, so you can figure out some sort of an association analysis between the 2 to figure out if I have a damage extension of 5, it's most likely that I have 3 or 4 lanes that are closed, and so on and so forth. So we looked at association rule, which is a machine learning tool to associate 2 things. It has 2 parameters in the association lane. One is the support, and one is the confidence. The support is this item set, in the database, between the 2 databases. And if the item set appears in the database, how many times did it appear in the database? So you have some sort of a form to put a probability to it. If I have a damage of 4, given this, I'm going to have so many lanes that are closed. So we looked at that, and so this is a sample of that. So you'll have a damage extent for, I have 2 vehicles, then most likely I have some sort of a number of lanes closed 2 with support of 0.15 and with confidence of 0.6, which is high. If you draw your threshold at a half, you're going to say, well, most likely if I have a damage extent of 4 with 2 vehicles, I have 2 lanes that are closed. So you more or less assign probabilities to that. And so if you have an incident with number of vehicles, one lane is 2 lanes. So you start assigning probabilities on how many lanes that you have closed in there. So now I looked at the traffic intensity, and I calculated the traffic coming into that section. Then I looked at the lane closure. So now I know the capacity of that highway with the lanes that are still in service. And now I started adding things that could really add to the delay, the time and stuff like that. For example, if you lost that lane, you know that the vehicles that are going on the closed lane are going to somehow maneuver into lanes that are going to be open for service. So that maneuver, there is a penalty to it that you can add, and that penalty is added to your time in the calculation. So that would allow us to more or less add some sort of a random type of delays that are being affected through the change of lane from one closed lane to an open lane. And so we took that information and started putting it in a queuing simulation. And so we fed the queuing a damage extent, of course, because we need to calculate for the capacity impairment that happened after, number of lanes of the highway, vehicles involved, type of collision that have. We took the average time, and then as the intensity changes per peak hour, off-peak hour, we adjusted for that in there. Then we adjusted, based on these measurements, adjusted the service time of that highway. I lost 2 lanes. And so I lost, really, if it's a 4-lane highway, so I lost, equal to half of the capacity of that highway. And so you adjust that based on loss of that capacity. Now your service time for that section is more or less increased by that much time that is being calculated in the simulation. So then duration of the incident, you put reporting time, response time, and the clearance time. So you put that you enter that information into that model, and then after that, you have now parameters that you can feed it into the simulation. And once you feed it into the simulation, it's going to give you an average queue length during an incident, an average waiting time within the queue, an average time clearing time. So those are the outcome of that simulation that gives you, now the spatial, you know how many vehicles, average vehicles in that queue, so you can calculate the space that is going to grow as time goes on. And then you have now the time that you can add within which, any accident could be considered a secondary accident. So we run these onto given our database that we have been given by the traffic engineering. And so you can see that it would block that in the distance domain and the time domain in there. So you'll have a kilometers and hours, and you'll see that given that location of that, let's see, where is that? There should be a note there, a legend, but given the highway, I think it's I-40 highway there, and given the location of that, given the time of that, you'll see that the queue grow tremendously, in there, six kilometers, and you have a timing sequence for that, within which we identify a secondary accident, not just one, as an example. So we took all of that data that we have and manually figured out, the secondary and the primary and the secondary, and then we fed it into some sort of an ANN, an artificial neural network, to figure out, would that ANN model be able to detect on its own the ones that are secondary versus primary. So the data that we collected that we have is we entered into our model 8 parameters: collision time, number of vehicle involved, commercial vehicle involved, number of lanes in the highway in that segment, damage extent, you have 0, none, all the way to 5, which is fatality in there, average traffic. Usually the police reports have an average traffic there right in there, so we took that, although ODOT has ABC in many locations here, so you can get much more accurate in terms of the numbers and so on for traffic for a given time in periods of 15 minutes. So we could use this data in here instead of using that guesstimation, I guess, in there. So then the weather condition at the time as it registered from 0, 1 clear all the way to 9 blowing sand and soil and dirt and so on. So you'll have all these cloudy rain, snow, and so on. Light condition is it daylight, unlight, lighted, dawn, dusk, and so on. So we took that and we just generated a simple 3-layer ANN and fed it with 8, this should be 8, the 8 features that we have, and you have only one hidden layer, and then you train this network in there to give you an output. Is it a secondary or it's not? Okay, is this accident is a secondary or not, based on these characteristics that I just listed, the 8 of them in there. And so you'll have the weights, if you're familiar with the ANN, you have weights for the input of the hidden terminal, and you have weights into the output of the hidden terminals. And these weights, as you train, they get converged to a value to give you an accurate outcome. So when you train, you tell them, I'm training you for a secondary accident, and you keep on feeding it the data, and more or less it converges to those weights, and the outcome would be between 0 to 1, and you put that. And so when we did and applied that on a data that have not been processed manually, we have achieved an accuracy of 91%. And I'll give you that the sample that we had, because we had to match the data from the incident report from ITS to the data from the traffic engineering, and we did not match as many as we would like. But even with that we used and trained, we were able to achieve an accuracy of 91% in there in detection of secondary accidents. And then for a precision, we had a 89% of precision detection, which is a true detection in there. So that's the modeling that we have done. So then we started looking into exactly what we want, how we wanted to incorporate it with the NPM RDS tools. And this is a data set that received from the data analyst, Daryl, Matthew, and so on, where you use that data to come up with the national performance measurements, indexes, congestions, and so on and so forth. And so we built that on the top of the database. We built tools that we would like ODOT to use to really more or less analyze. And now we're building all of the machine learning, data mining type of algorithms to detect events that are really not in the process. So for example, I just give you a process. By the way, there is a demonstration for all of that. If you're interested, there is a table with a computer, and Naeem is sitting here. You can just check with him and he'll tell you. But things of giving you visualization that is important for ODOT to detect things on the spot. And so the process is very fast. We're trying to make it way much faster than what we had, because we had a version 1, and now we're looking at version 2 that we are doing in there. And so if you look at this is a 1-month type of data that is a heat map. You'll see that there is a recurring congestion that happened, but then there is something that is not out of the norm. It's an abnormal. So with our algorithms, more or less immediately zooms out to things that are not normal. This is not something that I have seen before. This is something it's different. And even when it puts the window, you can put the window. We're looking at when you click on that even window, it just immediately zoom in, and it gives you the traffic. So it gives you more of a zoom in type of activities. It gives you the free flow of that segment, that particular segment. It gives you, from the free flow, we drop 3 standard deviation, and we call that as a congestion. So anything below the red line, you'll have more or less a congested in there. So that the NPM RDS is a huge tool, because you have access to all of this data that is provided by FHWA to ODOT, and that represent every highway segmented into many segments, and travel time for every segment is reported every 5 minutes. So that's a great data to start now mixing other things. As the director of the Texas A&M Transportation Center said, big data analysis. And that's a big data, really. You have a huge data. If I generate one year of one highway, it's like 80 gig of data. So how would you look inside that and look and match with the things that we're trying to do with the congestion? So here is an example of a secondary accident. And I'm really sorry, I have a hard time even seeing it myself, but anyway. So you have an accident. This is a backward meaning that a queue built up to the point where it caused the secondary accident. And so you'll have an accident at 1745, and you'll have an accident at 1825 on I-44, I think, highway. And you'll see the effect of that accident at this particular time, at this particular location, did not really have an effect. It did drop the speed, but it did not drop it enough to warrant any response to it in there. So you look at that. This is a backward. As I told you, the secondary might not be caused by a queue. It might be forward, where people wait in the queue, or they see the accident, they slow down, and then they zoom out of that, and it causes an accident. So they tend to go, and so that's a forward example for a forward accident. The accident happened 1813, but then the traffic is going that way, and that secondary happened at 1832 in there. Here is an example on I-44. You'll have a secondary. It's a backward, severe. You'll see that the severity of the primary 1, the severity of the secondary is 3. And as I said, the tendency is the secondary becomes more harder than the primary in there. And you look at so that's the line that reported by the police officer that this is where it occurred. But you look at it, it did not really occur at this time. It occurred earlier, but that's when they showed up and they start writing the reports and so on. And you'll see that between those two segments, they're not overlapping, they're separate segments. You'll see the damage that it has. You'll have, this is a whole, like this is the starting of a day, so it's early on at 8 o'clock, and it hit, and it until more or less after 12 o'clock, you still have a damage, congestions or delays due to that primary accident that happened, and then the secondary happened that caused a little bit more disturbance to that. Thank you. And so, but imagine now, given that we have the NPM RDS data, and it's really a post-processing type, so we get it at the end of every month. But imagine if we have it where it's really real-time coming from ODOT, because I think probably Alan Stevenson has access to real-time travel time. And so if you have that, you imagine yourself coming in, here is the traffic coming in. Could you please start it? I don't know if, yeah, thank you. So you'll have a free flow. We indicate a free flow. So we build a model to detect what type of flow. So it's a free flow, an incident detection, or a weather related, so snow or other related. And you'll see as the traffic comes in real time, immediately an indicator of an accident happened right away, that and the clearing, and now you have a starting time and ending time. So imagine this is really in real time, and as I gave you an example for this, the reported that is behind where the accident happened, you would be reacting really immediately at this time. So if I automate this process where I look at the travel time in real time and my model says that's an incident, you can really dispatch somebody to the site to clear the site immediately in lieu of waiting for a report or somebody calling in and so on and so forth. So that's the advantage of having real time, and that's hoping that this is something that we go to. But other analysis tools that we built on this, the more or less the display of all of these incidents on a particular highway for a particular time period. This is a level 5 fatality involved in this, so you can have these type of measurement. You can have incident severity, so you can study all of the traffic or incidents that have a severity higher than 5 and look at where they are located in there and what effect they had on traffic, and so you build according to that. And even you can look at the incident study itself without looking at the severity. So you look at the location, you put a location, and you look at the accidents that happen, and you see that immediately with these tools is going to provide you what direction it happened, the incident happened or accident happened, and did it have an effect on the other. So this tool that we are building, more or less hoping that they could use it or not use it to the analysis for secondary or accidents in the process. Now I'm going to skip all of the relationship, but we looked at what effect really factors influence secondary accidents. And what we saw, believe it or not, that commercial involvement of commercial, so the highest L5, which is moral dusk, have a good correlation for a secondary, a dusk. In L2, you'll have a no light, had a good correlation with accidents. W6, which is a sleet hail, has a good correlation for secondary accidents. Involvement of commercial vehicles has a clear indication of a factor of secondary accidents. And then damage extent had a clear indication of accidents. Acknowledgement, I really don't know who to thank here. I work with a lot of ODOT people, and I do thank and appreciate all of them. David Uten, Ron, Kerb, Teresa, Brian, Gary, all of this from the research office. My sponsors, Matthew, Daryl, Alan, in there, they give me the chance to talk with them, and they just nod their head. I don't know if they agree or not, but they nod their heads when I talk with them in there. With that, I really conclude my presentation. Thank you for your attention.
All right. I don't know if this works. We have time for one question. You want to pick one? Uh-oh.
Is the data from Waze and other map app features available?
We have not engaged Waze in there. The data that we get for the NPM RDS is here data from the, I'm sorry. So the data we have, the NPM RDS data, is really from INRIX since 2017, and prior to that was from here. So not Waze.